Section 1.2, 3 different types of machine learning. Earlier, there were 3 different types in machine learning. But nowadays, there are many different types in machine learning, so that we can say more than 3. However, if you understand the couple of different types, then you can understand the others quite easily. So we'll see here 3 different types. Number 1, supervised learning. Number 2, unsupervised learning. And number 3, reinforcement learning. Supervised learning is along with labeled data. And unsupervised learning is with data having no labels. And reinforcement learning is along with reward system. We'll see some details here. Okay, supervised learning, we are using labeled data, and a data set is given in this way: xi, yi. Xi is a vector, and yi is the label. For example, the vector is representing either human or cat. Then for human, the label can be 0. For cat, label can be 1. So that for vector, now it can be 1 or 0. And in this way, the vector representing some object is along with a label. So information is given. Now, the assumption for using such a data set is there is a relation between x and y. So there is a function from x to y. And human intelligence can say easily, if you see a picture of a human, then you can say it's a human, so answer is 0. And if you see a picture of a cat, then you can say 1, like that. So there is a relation. So we assume such a relation. Now, with supervised learning, by using data set, if it is used for training, then it's called the training data set. So here there are n vectors and attached n label values. Using the data set, we try to find f hat from x to y, a good approximation of f. So that is supervised learning. Here pictorially we can say that the training data has a label. And here, by using machine learning algorithms, we can produce predictive model, that is f hat here. So that in this picture, this predictive model is now f hat. Okay. Once it is made as good approximation of f, then new data point is coming in. And then by using the new data point, we can say is either 0 or 1. So that is called the prediction. So that is how supervised learning is organized. So in practice, for example, this is a points of negative, the points of positive. So there are 2 classes. Now, once you can find a line between them, then, and as a new point comes so that it is that side, then we can say this is one of a negative. If a point goes to this side, then it is one of a positive, and so on. So in practice, in supervised learning, we are trying to construct such separator. Right now, this is a line, But in more complicated algorithms, you can make really more complicated curve separating two data sets. And this is another machine learning algorithm, and there is a regression. That is basically for given data set, we try to find here representation. Okay, that is regression, and this side is called classification. Okay, here let's consider this example. Here we are trying to get 10 points from sine curve from axis from 0 to 1, and that is sine pi x, in fact sine 2 pi x, and out of that, and we choose some points on the curve and randomly perturb a little bit, so noise is added. And using these data points, we try to find the regression model. That means we try to find a polynomial particularly. So here now, that is hypothesis space. So we try to choose a space for the model. That is called a hypothesis space. And now we choose the polynomials, degree m. Now here, once for those data points, you are choosing polynomial of degree 0, which means constant. Then that is best fitting constant. And once you choose m equal 1, so it's linear, then that is best fitting line. And in this way, if you're choosing m equal 3, so it's a cubic polynomial, then this is best fitting cubic polynomial. If you are choosing m is 9, then there are 10 points, so that you can here find a polynomial. In fact, this is unique polynomial passing through this all 10 points. But now here, that is oscillatory. Okay, for that one, here we try to measure the error. Here now, along with this, using a misfit function, for example, the square error, and that is empirical loss function. And here, this square distance is now added and divided by n. So it is average the misfit, square misfit. Okay. That is now empirical loss function, or sometimes it's called cost function, and having mean square error. Okay. Okay, here now, and we try to get another set. Again, along the original curve, we try to find, we choose random points and perturb along with same manner. And we try to now measure the distance from this produced curve. Then we can find here now the error in this way. This blue one is error along with training points. Training points. Here now, if once you make this one, then from here you can measure the error by using the function and error, and for 1, m equal 1, you can also measure the distance squared, the distance squared, and sum, and divided by n, divided by 10. So that you can get error for each curve. And along with this training point, the error is given in this way. So that once m is 9, then because the curve is passing every point, error will be 0. However, if you are making the similar kind of data points after construction of the polynomial, then try to measure the distance from the curve to new data points. Then now here it cannot be 0. In fact, this is huge, very large. That means that right now you are feeding here too much. So it is called overfeeding the data points. But once similar kind of data points coming in, then error can be larger. So this is one example of overfeeding. Now here from 3, m is 3 up to 9, the error is constant. In this case, we can choose m is 3 as the best concise model. So for this example, and hypothesis space, the best one is P3, the third order of the polynomials. Okay, so we'll see here now. Okay, training and test performances. Okay, here and earlier we used the least square error for training loss. So that is basically called empirical loss, and also sometimes called empirical risk. But in fact, rather than training data set and for new data set, this means that and not yet available. However, in real life, if the machine learning algorithm is used, then new data point will be coming, so that by using the due data point, and expected loss can be defined, so that ideally we have to minimize the risk rather than empirical risk. However, it is impossible to compute it because the data points are not yet available. However, here the empirical risk is good estimate of the original, the expected risk, so that we try to minimize empirical risk. So the principle of empirical risk minimization can be formulated in this way. Here, try to find the model to the data, so that is minimizing the given the empirical risk function. Okay. Okay. Here we have key issues in machine learning. Here, first issue is how do we choose a hypothesis space? And as in here, the example of regression, and after doing practical computation, we can choose a 3 to 9. The accuracy is not improving, so that in this case we have to choose a simpler one, so that it's cheaper to get the model. Okay, but anyway, the question is how to choose such a space. And maybe right now we chose polynomial space, but we may try to choose some other space. But by using some prior knowledge, we can choose. For the example of regression, we can choose, for example, some sine curve, then maybe it's better. And once it is chosen, then how can estimate the accuracy of a hypothesis is also a very good topic. And so that choosing hypothesis space, and now once it's chosen, then how to measure the accuracy of a hypothesis is also another issue. And also here now, how to find the best hypothesis is also a big issue. Okay, we'll deal with these issues during the lectures. Okay, here we have a proposition that's called the Occam's razor principle. One should not increase beyond what is necessary the number of entities required to explain anything. That means that once you try to choose hypothesis space, then try to choose a simple one. Once they have a same accuracy, then try to choose a simple one. So of course here, the meaning of a simple is not clear at this moment, but later on we'll see what it is. And usually we have to use prior knowledge to solve the issue. Okay. And also one example of a prior is smoothness. We try to get the model as smooth as possible, and also we try to make it as accurate as possible in real world. Okay, now we'll go to unsupervised learning. Unsupervised learning is using data unlabeled. There's no label, and so that the algorithm will try to explore the structure of a data set. So eventually, we try to extract meaningful information without using any guidance or without using any earlier knowledge. And here, one example is clustering. And for example, once these points are given, then we can make 30 groups of the points, so that these 30 clusters through clustering, by using clustering algorithm, is really quite understandable. And then now here, with this one, we can say that the data set has 30 different groups of points. And that is a sort of exploration of the structure in the data set. And out of that, we may try to extract some meaningful information. And with a label, we can do something useful. Okay, that's the end of the section. Thank you.